Okay, so we are talking about eigenvector. So, just to recap, we will discuss the geometric multiplicity of a eigenvector. So, just to recap, so we have a matrix, square matrix, n cross n square matrix. Then we called a non-zero vector to be eigenvector of this matrix if x is non-zero, and this system has a lambda, this system has a non-zero solution, and that and we have seen also if we have a eigen. So, this is corresponding to a, so a eigenvector is corresponding to a unique eigenvalue, and for a eigenvalue we could have a many eigenvector, but it should be from the same field where these ai's are coming from, like if A is aij n cross n, and if the matrix element are coming from the field this, then this eigenvector should be coming from this is a n tuple where each of x I is f. So, this is so basically x t is belongs to f to the power n, but there must be from the same field. So, now we will take an example of a real matrix where eigenvector does not exist because of field. So, let us take an example. So, suppose our field is the real field, and we have a matrix like this 0 minus 1 1 0. So, what is the characteristics polynomial? Characteristics polynomial is x square plus 1. So, characteristics equation is this. So, we have seen this example in the last class. So, we have two eigenvalues, this is a complex number. So, these eigenvalues are complex. So, so eigenvalues are complex. So, that means this implies there is no eigenvector exist in the real field, because our underlying field is real, but if we allow to have the complex field, then we will come to that. So, no eigenvectors in the real field. So, no eigenvector exists in that case, but if we allow our field to be the complex field, then we can find the eigenvector corresponding to these eigenvalues. So, let us take this matrix again, and now our field is a complex field, set of all complex number, and we have two eigenvalues, lambda 1 is equal to I, lambda 2 is equal to minus I, plus minus I, two eigenvalues. So, now we want to find the eigenvector corresponding to these two. So, eigenvector corresponding to lambda 1, which is I. How to find? This is a set of all non-zero vector such that set of all non-zero vector. So, now they are coming from complex such that A x equal to lambda 1. So, lambda 1 is I x. So, this if we simplify, we will get the homogeneous equation like this 0 minus I minus 1 1 0 minus I x 1 x 2 equal to 0 0. So, that will give us x 1 equal to I x 2. So, that means if we took x 2 to be k, any complex number, then x 1 is k I. So, that means eigenvector are of this form. So, one is k, no, x 1 is k I and x 2 is k. So, this is of the form I. Okay. So, this set if we vary k is a complex number. So, this set is called the eigenvector. We can corresponding to the eigenvalue. This is the set of all vector like this, where k is a complex number. Okay. So, this is the eigenvector corresponding to this. Similarly, we can find the eigenvector corresponding to other eigenvalue. So, corresponding to lambda 2, which is minus I. If we do that, we will get the equation like this, 0 plus I minus 1, 1, 0 plus I, x 1 x 2 equal to 0 0. So, this will give us something like x 2 is equal to k and x 1 equal to minus k I. So, this is basically the set. So, this is eigenvector, we can write V actually. So, this is a set of k into minus I 1, where k are coming from the complex field. So, this is the eigenvector. So, these are the eigenvectors corresponding to this. Okay. So, now we will get some result on the eigenvector. So, if we have two eigenvector which is corresponding to two distinct eigenvalues, then they are independent. So, this is a theorem. Again, suppose A is a square matrix, A are coming from the field, A are coming from the field Aij if, okay. And suppose you have two eigenvector x 1 corresponding to lambda 1 and x 2 corresponding to lambda 2. We have two eigenvector, they are corresponding to two distinct eigenvalues such that lambda 1 is not equal to lambda 2, and these xi's are coming from x 1 and x 2 are coming from the n tuple of the field, their elements are from the fields. Okay, this is the n tuple. Okay. So, now our claim is these two are independent, x 1 and x 2 are linearly independent set of vectors, linearly independent over this. So, how to show that? To show that, we need to take a linear combination of this, and you have to show how to show two vectors are linearly independent. So, we have to take alpha x 1 bar plus beta x 2 bar, and if we have to equate to 0, if this implies alpha equal to 0 equal to beta, then this is the linearly independent set of vectors. Okay. You can take a column wise also, does not matter. So, now we take, now to prove this linearly independent set of vector, what we do? We just apply, so we have in column wise, if we take alpha x 1 plus beta x 2, we are taking this is 0, this is a column vector. Now, we know that A x 1 equal to lambda 1 x 1, A x 2 equal to lambda 2 x 2. So, now if we apply A on this, so A lambda x 1 plus B alpha A x 1 plus beta A x 2, this is 0 vector. Now, so now this is one equations. Now, if we just alpha A beta y. Now, alpha this is give us what? This is the alpha lambda 1 x 1 plus this is A x 2 is lambda 2 beta lambda 2 x 2 equal to 0. Now, if you multiply this with lambda 1, then we get alpha lambda 1 x1 plus beta. We are multiplying this with lambda 1 x2 equal to 0. So, if you subtract this is cancel out, this is beta into lambda 2 minus lambda 1 x2 equal to 0. But here none of them are 0, x2 is non-zero vector and these are distinct, we assume. So, this gives beta equal to 0. Similarly, if we multiply this with lambda 2 and if we subtract, we will get beta equal to 0, we will get alpha equal to 0. So, that means these two are set are linearly independent, x1 and x2 are linearly independent set of vectors. So, any two vector which are corresponding to the distinct eigenvalues, they are independent. So, this result hold for more than 2 also. So, if we have 3 eigenvectors corresponding to 3 distinct eigenvalues. So, if we have say x 1 corresponding to lambda 1, x 2 corresponding to lambda 2, x 3 corresponding to lambda 3. If we have more also x k corresponding to lambda k's, and if they are distinct, if lambdas k are distinct, if lambda is not equal to lambda j or I not equal to j, that means this set, this is corresponding to distinct eigenvalues, then this set is a linearly independent set of vectors. Then this set is linearly independent set of vectors. Okay. We prove for 2, we can extend it for more than 2 by the help of even for the induction or inductive proof we can do. Okay. So, now this is one observation, and now we are going to define the geometric multiplicity of a eigen value. For that we need to bring the vector space, subspace. So, let us have the okay. Now, say A is an n cross n matrix coming from the field F, and let lambda be an eigen value of A. Okay. So, it has many eigenvectors. So, that eigenvector we take it as this. So, this is the set of all non-zero vectors. These are coming from the same field such that A x equal to lambda x. This is an infinite set we have seen. Now, if we add this with, if we take this vector v, which is if we add the 0 vectors, because 0 is obviously has a, will satisfy this, then this is a, I mean if we take the transpose of this is a subspace, this is a vector space, and vector space, this is a subset of v to the power n, I mean transpose of that v to, f to the power n tuples. Okay. So, and we know this is a vector space. Now, this is a subset. Now, when we can say a subset is again from a vector space, we have some necessary and sufficient condition, we will come to that. So, we have to show this is a, this V along with this is a subspace of this. Okay. And the dimension of that subspace is nothing but the geometric multiplicity of this lambda. So, first of all you have to show this is a subspace. So, how to show this is a subspace? Okay. So, to show subspace we need to take two vector from this. So, let us have the vector space again. So, this is nothing but the set X. We can take the transpose if we are comfortable with the row or column vector, but anyway these are the notation. So, X such that X is non-zero, such that A x equal to lambda x, and we include the 0 vector, because 0 is obviously a solution of this. Now, if you take x 1 and x 2 from this two vector x 1 and x 2 from this, and if we can show alpha x 1 plus beta x 2 also belongs to this, and if this is true for all such x 1 x 2 and for all the scalar this, then this was a next, if you remember the vector space subspace, there we proved that this is a condition, necessary and sufficient condition to a subset to be become again a vector space under the same two operations. Anyway, so we have to show this. So, how to show this? So, to get this we have to do a, so this is say this is y. So, we have to show y is belongs to this. So, for that we need to show a y is equal to lambda y. If we can show that, then y belongs to, y is again a vector space, eigen vector. So, what is a y? A in alpha x 1 plus beta x 2. So, this we can write alpha a x 1, alpha beta is the scalar. Now, these two are eigen vector corresponding to eigen value lambda. So, this is nothing but lambda x 1 plus beta lambda x 2. So, we take lambda common. So, this is alpha x 1 plus beta x 2. So, this is lambda y. So, a lambda y is equal to lambda y. So, that means y is again a, y is either 0 or it is again a eigen vector corresponding to lambda. So, this result is true. So, this implies that V is a vector space, which is a subspace basically, because this is a subset of the f to the power n, and the dimension of this vector space is defined as geometric multiplicity of lambda. The dimension must be less than n, less than equal to n, because n is the dimension of the f n, and it is a subspace. So, dimension has to be less than n. So, that is the geometric multiplicity of the eigen value lambda. So, the dimension of V is called geometric multiplicity of lambda. We know the algebraic multiplicity. Algebraic multiplicity is the number of times lambda is coming in the roots of the this polynomial characteristics equation. So, that was the algebraic multiplicity. What was the algebraic? If this is the, if this was the characteristics equation, then if lambda is eigen value, then lambda will be the root of this equation. So, if it is coming, if the root is of multiplicity r, so that means lambda coming r times in the root. So, then we must write x minus lambda to the power r, then some other polynomial where phi of lambda is not equal to 0, because r is, then r is called algebraic multiplicity. R is called the algebraic multiplicity of lambda. Okay. And this dimension of this vector space is called geometric multiplicity of lambda. So, we have a result that is called if r is 1, that means if the lambda, if the r is the lambda is the root with multiplicity 1, then lambda is called simple eigenvalue. Simple eigenvalue. Okay, and we have a result for geometric algebraic multiplicity. So, that result is telling us that geometric multiplicity is less than or equal to algebraic multiplicity. We will get the geometric algebraic multiplicity over through an example. So, this theorem is telling, so suppose A is an n by n matrix and lambda is an eigenvalue of A, any eigenvalue, then we have this result 1 less than geometric multiplicity of lambda is less than algebraic multiplicity. Of lambda. Okay. We are not going to prove this, proof is there in the textbook. So, geometric multiplicity is always less than equal to, these are all less than equal to algebraic multiplicity, and lambda is called a regular eigenvalue if these two are same. Lambda is called a regular eigenvalue if geometric multiplicity of lambda is same as algebraic multiplicity of lambda. If the geometric multiplicity of lambda is equal to algebraic multiplicity of lambda, then it is called a regular eigenvalue. Okay. We will take an example and we will find the both the multiplicity for a given matrix A. So, let us take an example. So, we take a matrix over the real 1 1 1 minus 1 minus 1 minus 1 0 0 1. So, we take this matrix. Now, we have to find the eigenvectors or eigenvalues of this matrix. So, for that we need to construct the corresponding characteristics polynomial and characteristics equation. So, characteristics polynomial is nothing but A minus x I. So, determinant characteristic equation is giving us this. So, this is nothing but 1 minus x 1 1, then minus 1 minus x, then this is minus 1 and 0 0 1 minus x. So, this determinant is 0. So, if you solve this, it will give us the, if we calculate this determinant 1 minus x into x square equal to 0. So, this is giving us the solutions x equal to 0 0 1. So, it has two distinct eigenvalues 0 and 1, and 0 is coming twice. So, this root are 0 and 1. So, the roots multiplicity of 0 is 2. So, that is the algebraic multiplicity, and geometric and the algebraic multiplicity of 1 is 1. Okay. So, that is the, so we have two eigenvalue, two distinct eigenvalue, lambda 1 is equal to 0, lambda 1 0 with algebraic multiplicity 2 and lambda 2 equal to 1 with algebraic multiplicity 1. Okay. So, so these are the algebraic multiplicity. So, in the next class we will discuss the we will find the geometric multiplicity of this eigenvalue. So, we have two distinct eigenvalues 0 and 1. So, we will discuss the geometric multiplicity of these two eigenvalues, and for that we need to take the set of the vectors, the eigenvectors corresponding to this eigenvalue, that we will discuss in the next class. Thank you.